Okay, welcome to today's questions and answers session. We'll wait one more minute to give everybody a chance to join as usual. But while you're waiting, of course, you're invited to already submit your questions here. As usual, we'll use the channel for the central exercise session, this one, on chat.tum.de. So please log in there using your TUM Online credentials, choose this channel, and you can ask your questions on that channel. Again, we'll wait one more minute and then we'll start the Q&A session. Okay, I guess we can start. For those of you who just joined, welcome to our Q&A session. As usual with the central exercises, please ask your questions on chat. We use chat.tum.de. You can just log in with your TUM Online credentials there. And then please use this channel here, MA9714-CE, to ask your questions. As usual, we have a moderator who will be taking your questions and forward them to me. Kathleen, would you introduce yourself, please?
Yeah, sure. Hey, I'm Katrin. I'm a math student, and yeah, I'll be the co-host today.
Okay, thanks a lot. Before we start, one little service announcement. For those who have not noticed, the prep exam is now open on TUM Exam. Please remember, if you want to take the exam, the first exam, then this preparatory exam is mandatory for you to take first. Submission is possible from today until Sunday, August the 9th. So please complete this preparatory exam and upload it on the TUM Exam platform. You can find the link for accessing the exam on TUM Online. Just have a look at the exam for this lecture and have a look at the information column. There should be a link. Follow that link and you should be able to access the TUM Exam platform and complete this exam there. Again, it's mandatory to take this. I will not be able to register you for the actual one-time exercise if you don't take this mandatory exam first. Okay, so let's see what questions you have. Katrin.
Would you like to start with a question on the exam or something on the content?
So maybe let's get the organizational questions out of the way first.
Okay, so there is a question from Marcel Gilg. Do we have a disadvantage when we use a non-programmable calculator like Casio in the exam?
Although calculators are allowed in the exam, I can assure you, you won't actually need one. So no, you won't have a disadvantage.
And until now, there is no more question on the exam.
Good, so let's start with the actual questions then, and
Okay.
any other questions pertaining to the exam, we'll just treat those at the end then.
Yeah. So I would like to start with the first question from Leonard Speer. Could you please explain how to do the parameter form when computing the tangential plane?
The parameter form when computing the tangential plane. I'm not quite sure whether I get this question.
Well, there's written parameter from when computing the tangential plane, but I think it's a typo. Parameter form instead.
Okay, let's see if I can get this right. So when we're computing a tangential plane, let's say we're probably thinking of a function of two variables, let's say. I just do two variables. It's mostly the same for all, but two is easiest. So that has, let's just take something like this, x1 squared plus x2 squared, yeah, to give you an easy example here. And if you want to have a tangential plane at a certain point, let's just say we take the point 0. Again, just for ease of notation, any other point will work as well. And basically what that means is you're computing a Taylor approximation of order 1. Yeah, so order 0 would mean approximating by a constant. Order 1 is approximation by a plane. Order 2 would be by a parabolic surface, and so on. So we want to compute the Taylor approximation of order 1. Basically what that means is we have to compute both the function value at the point in question, it's just 0 in this case, and we also need the gradient of the function. And the gradient, that would be 2x1, 2x2. So at the point 0, the gradient would again be 0. That's maybe not such a good example, actually. Yeah, but doesn't really matter much. Okay, so what we get here as the tangential plane I'll change the example in a minute just to complete this, is actually the plane that is constant 0, right? So this Taylor approximation T1 of f at the point 0, 0, it is just 0, meaning if I draw this like this, right? We have x1 here, x2 here, x3 here, then this tangential plane is simply this x1, x2 plane here, right? So that's what happens here. Let's make things a little more interesting, maybe. Or actually, we can use this as well. Yeah, let's stay with this one. You can make this more interesting yourself. So how to describe that plane here? There's two options that you can use here. You can either resort to the description of this plane using a normal vector, or you can describe it in parameter form. And I'm guessing that's what you mean here, the conversion from normal form to primary form and vice versa. So in this case, what we have to do is we need to find a normal vector for that plane if you want to use normal form. Normal vector for that plane here is, of course, easily found. For example, you could just take this vector here. Yeah, that extends the x3 axis down. You can also go upwards. It doesn't really matter for the plane. So let's just go downwards. What we get here is then the vector, so the normal vector here for that plane. That would be 0, 0 in x1 and x2 direction, and then we can just add a -1 for x3 direction. And you notice this first part here, that is the gradient of f at the point in question. Okay, so you can use that to get the normal vector for that plane. And then in this case, the normal form of that plane normal form of the tangential plane. That would then be, just get this vector here, 0, 0, -1, transposed x1, x2, x3, equals, in this case, 0, 0, 0, because the plane contains the origin. If it didn't contain the origin, you would just take any point, compute this scalar product here, and use the resulting value. Oh, sorry, the resulting value is of course not a vector, but a scalar, sorry. And use the resulting value here as the right-hand side. Now let's say we have a plane that is given in this form, and we want to convert it to parameter form. Then what do we do? Basically, the idea here is, with this normal form description, what you're saying is, I'm describing the plane as the set of all points that are perpendicular to this vector here. Right? That's the description of normal form. In parameter form, what you would do is, you would explicitly describe the plane as the set of all points that are given as the span of two vectors. So what we need to do is, we need to find two vectors in that plane. Doesn't really matter which. Any two that are linearly independent will do. And we just say the plane is the span of these two vectors. If the plane does not go through 0, then we might have to add some translation to that. Yeah, but in this case, it's just those two vectors. So what we do here is we find any two vectors in the plane. We need to make sure that they are linearly independent, and then we can just use those for our parameter form. So what we do is find two linearly independent vectors in the plane. And in this case, you could just have a look at this form here and take a guess. It's probably the easiest you can do. Just find two vectors that satisfy this equation and that look linearly independent. And I mean, this linearly independent is not hard to get. For example, you could start by trying, let's say we set x1 to 1 and also x2 to 0. And for the next one, we do x1 equals 0 and x2 equals 1, and then we have guaranteed that the two resultant vectors will be linearly independent. Of course, that's just a guess at this point. Yeah. So the question is, can we supply an x3 coordinate that fulfills this equation for both of these two x1, x2 coordinates? So in this case, the scalar product of 1, 0 with 0, 0 is of course 0. So we'll have to set x3 to 0 as well to get the desired result here. Yeah. So the only possible extension here would be a 0. Now this vector here, if we multiply this with our normal vector, 0, 0, -1, then the result is obviously 0. So that's okay. Same thing for the second vector. 0, 1 times 0, 0 is 0. So we need to set x3 to 0 again. So that this actually works. Yeah, and again, if we substitute that vector here into the equation for that plane. We again get 0, so that's good. So that means we have two vectors that are linearly independent and in the plane. And that in turn means the span of these two vectors will describe the plane. So the tangential plane is then simply the span of 1, 0, 0 and 0, 1, 0. Or in explicit form, we could say the plane is the set of all lambda times the first vector plus mu times the second vector, where lambda and mu are both real numbers. Okay, so basically it was an easy example, but the idea is always the same. You have the normal equation for the plane. And what you basically do is you guess two vectors that lie in the plane, and then you write the plane as the span of these two vectors. That's your parameter form. I hope that was the question you actually wanted to ask. If not, just try it again.
There is a similar question, and I think you've just answered it, from Julius Mears. How do we generally find the normal representation of a plane?
Given what?
There is nothing written more.
Maybe
Sorry.
you could extend that question. How do I generally find the normal representation of a plane? Of course, I need something to start with. How is the plane defined?
So it might be that the question is on sheet 4, number 6, because there was another question on that, and there is a function given with the matrix.
So sheet 4, number 6 is it? Let me just try to see if I find this. Okay, sheet 4, number 6, yeah.
And I think that the question was concerning that exercise.
So in that exercise, I think we've started with a normal form. And then we proceeded to compute the parameter form. So the question is how to get the normal form basically from the Taylor approximation then, I'm guessing.
I can't tell you.
Is that right, Mr. Mears?
Yes, it is.
Okay. So let's see.
From Taylor to normal.
From Taylor to normal. Okay, so let's say we have Taylor. I'm just using the example we have here so that we have interesting numbers and I don't have to make it up on the fly. So for this example, basically we had a function R2 to R, and all you need to know is the Taylor approximation at this point. So the gradient, the question was for the tangential plane at the point 1, 1. So we want the gradient at 1, 1. And that gradient at 1, 1 is 5, 9 in this example. And of course, we want the function value at 1, 1. That should also be somewhere on here. That should be 7, right? Yes. Okay, so that means the Taylor approximation of f at the point 1, 1 would then be 7 plus 5 x1 minus 1 plus 9, not 7, plus 9 x2 minus 1, right? That's the Taylor approximation of order 1, given this data above. Now, how do we get the normal form from that? Well, basically what that says is every point on the plane that we're looking for is described by this equation. So here's the x1 value, here's the x2 value, and this is the corresponding x3 value, the function value of that Taylor approximation function, right? The graph of that Taylor approximation function is the plane that we want. So for that plane, the following equation has to hold. The equation is x3, the function value, is equal to 7 plus 5x1 minus 1 plus 9x2 minus 1. That's just the functional equation of that graph right now.
Michael,
Yeah?
we can't see your writing.
Oh, you can't see my writing. I'm sorry.
No.
Is it back?
Yeah, no, I see.
Okay, let me just move that to some other screen. Just a second. Obviously, I can't view two different screens at the same time. You can still see that? Okay, good. Where did I lose you?
Just when you started to write.
At the very beginning. Okay, great. Okay, so let's start over. So we want a Taylor approximation for a given function of order 1. And let's just say we have computed the gradient of f at the point 1, 1. We want the approximation at 1, 1. The gradient is 5, 9. And we have the function value that is 7. So the Taylor approximation is this. You can just compute that using Taylor's formula. This is the Taylor approximation of order 1. So that means that describes a plane. The graph of that function is a plane. That's the plane we're looking for. So what we want is the graph of this T1. Now what that means is we want all points that lie on that graph, and the points on the graph are characterized by their x1 and x2 coordinates, and the corresponding x3 coordinate is just the function value. So that's x3 here, this value. So in other words, a point is on that plane if and only if it fulfills this equation here. x3 is the value we get by computing this Taylor approximation. So now we have a description of that plane as an equation. And that basically is what we want for normal form, right? We just have to reformulate that a little to see that. Let's say we put all the x on one side and all the constants without an x on the other side. Then we get something like 5x1 plus 9x2 minus x3 equals, let's see, that's minus 7 plus 5 plus 9. So that should be 7, okay? Yeah. Okay, and this is an equation in normal form because we could just reformulate that as saying, well, this is the same as the scalar product of the vector 5, 9, minus 1 transposed x1, x2, x3, like this, is 7. So this is the normal vector that we were looking for. And if you compare that with our gradient, you will hopefully find, gradient was this here, 5, 9. You will find that actually, again, this gradient is the first two coordinates, and then we just add a minus 1. And that's the same thing we did before, if you remember that. Yeah, we just took the gradient, we added a minus 1 to get a vector that points down in x3 direction. So it is below that tangential plane. So same thing happens here. You can either just use that knowledge and take the gradient at a minus 1, or you can take the Taylor approximation and say, well, my x3 value is the function value here, and I just reformulate that a little, get an equation that I can write in this normal form here, and I'm done as well. Advantage of that one is it gives you the right-hand side right away. You don't have to do any additional work here. Okay, so that's how you can achieve normal form. I hope that answers your question. Again, if not, just write again.
There is a question concerning exercise sheet 11. Leonard Speer asks whether you can explain how to evaluate the set over the integral.
Which question?
11.6 and 11.7.
11.6 and 11.7. The volume of a solid body. And what is the question again?
It is, could you please explain how to evaluate set B in exercise 6 and 7?
How to evaluate set B. So you mean how did I come up with set B, I guess?
I think so, yeah.
Okay, let's see. Okay, so in 11.6, let's have a look at that one first. And I'm guessing 11.7 is similar. So what we're doing here is we're computing a volume of a solid body that is bounded by some surface and the plane. And the plane, that's the easiest part. The plane is described as x3 equals 8. And then there is the surface x3 equals 2 x1 squared plus 2 x2 squared, or just 2 x1 squared plus x2 squared. Okay. So what we want here, let's see. What we want here is a radius, sorry, is a body that is described by these coordinates. So basically what we have is a plane that bounds this. That's plane x3 equals 8. So let's say this is the x3 axis. There's 8. There's a plane going through there that will bound that body. And then we have the surface here. x3 equals 2 x1 squared plus 2 x2 squared. That's a little more complicated, I guess. So if you're familiar with polar coordinates, then you realize that this one here is exactly the radius squared of a point in the x1, x2 plane, right? So this plane here is a relation between the radius of a point and its height, in a way. And that is why we use cylindrical coordinates to describe this set here. Because those are an excellent way to have this relation between a radius and a height. What you basically do with cylindrical coordinates is you have polar coordinates in the plane. So you have an angle and you have a radius here in the plane, and then just add an x3 coordinate height to that point. Okay, so that's what we're doing here. And what this equation here means in polar or in cylindrical coordinates is the x3 is basically the same as the height of a function or of a point. So the height is exactly equal to 2 r squared. Or in other words, if you want to solve this for the radius, that's what I did here. The radius is the same as the square root of h over 2. So what I'm saying is height and radius are related for one of those bounds, right? So I can either take the height as the independent variable and then constrain the radius, or I can take the radius as the independent variable and then constrain the height. I opted for the first way, but of course you can do it the other way as well. Now what we're doing is the body that we're looking at rotates around the x3 axis. It does basically one complete rotation. It's a solid body. So our set B here would then be described by cylindrical coordinates through radius, angle, and height. For the angle, we allow one complete rotation. So we have the angle between 0 and 2 pi. Then we say we treat the height as the independent variable. So that means that would be between 0, between the x1 is 2 plane, and the upper bound, which is this plane here, yeah, with a height of 8. And finally, we need to put in the constraints between height and radius. And that is what we do last. So the radius is always greater or equal to 0, of course. And then it's constrained above by the square root of the height over 2, because that is what we found out here. So that's the other constraint, and we need to be below that constraint. So that's how I came up with that set B here. And as I said, you can also treat the radius as independent variable and try to constrain the height then. It doesn't really matter. Give it a try. Might be a nice exercise.
There is another question to this exercise. How do you know that 0 is the lower bound to h?
Yeah, maybe that's not explicitly expressed in that problem statement. It should have been. I'm sorry about that. My bad. Any more questions?
Felix Fechner asks whether you could go through or summarize the conditions we need to check when we see to see whether a vector field is conservative or not.
To see whether a vector field is conservative or not. Oh.
Yep.
Sure. So we have a vector field. Basically, to see if it's conservative means, is it a gradient field? So does it have a potential? And it means there's basically two things you could use here. The first idea would be, would be to check for the potential. So given a vector field, I'll just make this two-dimensional, R2, R2. Given a vector field V, we could try to find a potential. So find some, let's call it capital F. That would then have to be a function that is defined, in this case, on R2 or on whatever R we have here, right? And it always maps to the real numbers, such that the gradient of F is equal to the vector field for all points X. And you would usually do this by trying successive integration. I mean, this condition here, nabla of F equals V of X, gives you conditions on the partial derivatives of capital F. So something like this. The first partial derivative is V1 of X. The second partial derivative is V2 of X. And you can just try to integrate any one of those. Get kind of a candidate function for that capital F that maybe still depends on the other variable that you didn't integrate for. And then you could try to substitute that candidate into the next relation and see if you can get conditions on the remaining part of that function. Again, you would probably have to do an integration to get that remaining function. And then that way you would either compute a potential, or you would at some point find that there is no possibility to do that. Yeah, so that's of course the preferred way if you actually want the potential. If you don't just need to know that it's a gradient field, but actually want the potential as well. That's one possibility. The other possibility would be to check the integrability conditions. And those integrability conditions, there's basically two things that you will have to check here. The first thing is the integrability conditions, those need to be satisfied for any conservative vector field. Yeah, so a vector field that doesn't satisfy those cannot be conservative. Integrability conditions basically means the mixed derivatives, mixed partial derivatives have to agree. So if you differentiate the first coordinate with respect to the second variable, that has to be the same as differentiating the second coordinate with respect to the first variable. So in this case, dv1 dx2 needs to be the same as dv2 dx1, yeah, for 2 dimensions. For more dimensions, of course, there's more mixed partial derivatives. Basically, you need to check every possible pair. All of these need to agree. What this basically means is the Jacobian has to be symmetric. The Jacobian of V has to be symmetric. The Jacobian of V, if V is a gradient field, then that Jacobian is the second or differential of second order of the potential, capital F. So basically, this is Schwarz's theorem. Those mixed derivatives need to agree if the function is continuously differentiable. Okay, so that needs to be satisfied for the vector field to possibly be conservative. If that is not satisfied, then you can be sure the vector field is not conservative. It's not sufficient, however, so there might be vector fields that might satisfy this on their domain, but are still not conservative. And the problem here is that you also have to check the domain. So you can only use this condition as a sufficient condition if the domain is simply connected. If it's not, then that means the integrability conditions alone don't tell you whether the vector field is conservative or not. If they're not fulfilled, then of course the field cannot be conservative. If they are fulfilled, but the domain is not simply connected, then you don't know anything. Yeah, anything might still happen. And simply connected domain basically means there's no holes in the domain, right? So formally, any closed curve can be contracted to a single point that is still in the domain. So even if you punch out one single point off on the origin, then the domain is not simply connected anymore. And of course, if you punch out more than just a single point, that's also not the case. Yeah, so there cannot be any holes in the domain. If those two hold, integrability conditions and simply connectedness, then V is conservative. And you know that without even computing a potential. On the other hand, that theorem does not give you a potential. So if you want one for whatever reason, to compute an integral, for example, then you're still not much better off than before. Okay, I hope that answers the question.
So I think there's a question also to that exercise, but I'm not sure whether I get the question. How could we generally define a hole?
How could we define a hole? Complicated question, actually. So you will notice I didn't make the statement very precise in the lecture, and that is for a reason, because it's not that easy to get that technically correct, and it's not that relevant to you. So basically what I mean by a hole is you have some subset of R2, and then you just exclude one single point, or maybe more than one single point, yeah? That's what I mean by a hole, and that's not a very good definition technically. I'm aware of that. But if you wanted to make this more precise, you would have to first define what you actually mean by contracting a curve. So you would have to define what it means to contract a curve by, basically the way you do this is you define a mapping on curves, so a mapping on mappings, and then you define continuity on that, which is easily done technically. And then you can just say, well, if I have a mapping that maps the set of curves, so the set of mappings to a mapping that is just a single point continuously, then that's a contraction. And if I can do this for any curve, there's no hole. And if I can't do this for some curve, then there is a hole. but as I said, we didn't go into this. So intuitively, a hole just means punching out one or more than one point of any set. That should be sufficient for everything that you will need.
There is a question on exercise 9.5. Can you explain the Slater condition once again?
9.5, let me pull that one up, the Slater condition. So basically, you need the Slater condition to apply the KKT theorem. And what that means, what the Slater condition means is basically there is a strict interior point in the feasible set. So in other words, the feasible set is not subdimensional. So for example, if you have a feasible set in the plane that is just a single point, like this here, then there is no strictly interior point here. Yeah, there's no point such that a disk of positive radius around that point would still be contained in the set. The set only consists of boundary points. And that means the Slater condition is not satisfied here. Same thing if you have a feasible set that looks like this, yeah, just a line in the plane, that also wouldn't have satisfied Slater condition. Usually you have sets that are fully dimensional, look like this, for example, yeah, or like this. And those all have strictly interior points, this one, for example, or this one here. And that means for these points, the conditions that describe the set are fulfilled with strict inequality. So equality of those conditions defining the set holds for the boundary points. So in this example, for that line here, the circle line, or in this example, that would be these 4 conditions here that describe the boundary line. And then Slater simply says, we need to have a point that satisfies all of these inequalities strictly, with strict inequality, and this green point here would be 1. Yeah, in this example here, you could have, so in this example here with that line, you could have like one inequality that says we need to be to the right of that line, and you could have a different inequality that says we need to be to the left of that line. And then the intersection of those sets would be the feasible set, and that would obviously be just the line itself. And any point on that line would not strictly fulfill this inequality and not strictly fulfill this inequality. It would just fulfill both with equality. So Slater would not be satisfied for that set of constraints. Usually it's not an issue, but you just have to check. So usually you just guess an interior point, put it into your function G, into a constraint function, and then see that it is strictly satisfied with strict inequality. I hope that helps.
There is another question on KKT.
Mm-hmm.
So Eri Akiyama asks for the differences between Jacobian matrix, the gradient, and the Hessian matrix. Not the calculation, but the meaning behind it, because in homework 9.2, Eri didn't understand why the homework solution used the Jacobian of f of x for the KKT instead of the gradient as it is defined in the lecture.
So basically the question is about the difference of the gradient and the Jacobian. Is that right?
Yeah, and the Hessian.
And the Hessian, yeah, okay. So if I have a function f defined on some r to the n that maps to r, then we define the gradient of that function as basically the partial derivatives, df dx1 to df dxn, yeah? That's the gradient, and we define that as a column vector. Now later, we looked at functions that map from Rn to Rm, and we defined the Jacobian of such a function. Basically, the idea was to represent G as a vector of functions, G1 to Gm, x1 to xn, x1 to xn, like this. And then we define the Jacobian by simply saying, well, jg of x consists of the partial derivatives of those partial functions. So the first row is the partial derivatives of g1. So gx1, let me copy that to the next page actually. Yeah, that kind of, yeah. Okay, so the partial derivative of g1 with respect to dx1, and then we just continue up to dxn. And we can do this for all the partial functions. So the next row is for g2, then for g3, and so on, up to gm. So the last row consists of the partial derivatives of gm. Like this, yeah? So this is the Jacobian of a function. And of course, one could apply the same concept to a function f that maps to R1, right? And if we do this, turns out the Jacobian of f, where there's just one partial function, f1 or f itself, yeah, there's only one coordinate here. So that means we only have one row, and that means the Jacobian will consist of one row and n columns. So what we get is df dx1, and so on to df dxn. And you will notice this is almost the same as the gradient, the only difference being that this is now a row vector instead of a column vector. So this is the gradient of f transposed. And that's basically the only difference. So formerly we defined gradients only for functions mapping to the real numbers and not to some higher dimensional space. And for those functions, the Jacobian and the gradient are almost identical. The only difference is the Jacobian is a row, the gradient is a column, but they are identical via transposition. And then the Hessian would be the second order derivative of such a function f that maps to the reals. That would again be a matrix. And basically that is the Jacobian of the gradient, right? So the Hessian of f of x, that would be the Jacobian. So basically you take the gradient, you differentiate that once more, that's your second order derivative. So the Jacobian of the gradient of f, like this, that would be the Hessian. I hope that sufficiently answers the question.
Yes, it does. So there are two questions on integrals. So on the one hand, it's not clear why sometimes when using polar coordinates, which bounds to use. So Henry Kainz, for example, asks why to use pi half and 2 pi as upper bound, or the other way around. And also another question.
To some specific problem?
Yeah. So it's 13.4 and 13.11. It's not clear which bounds to use.
Let me have a look at that. Yeah. The other question?
The other one is, let me just find it. Could you please explain the 13.11 why the integral range of phi is from 0 to 90 and not from 0 to 180 degree?
13.11.
Yeah.
This is about psi, right? The range of psi is the question here. Okay, so let's start with 13.11 then. So the statement here is we need to compute the integral of a certain function over the upper half of a ball of radius 2 around the origin, and we should use spherical coordinates for that. So the upper half of the ball, like basically what we have here is something looks like this. There's a ball, and we want the upper half, anything that's above this x1, x2 plane, right? So how do we describe that in spherical coordinates? What spherical coordinates do, let's see if I can make a quick sketch of that. x1, x2, x3. So basically what we have with these spherical coordinates is a radius and two angles. The first angle and the radius basically as well, they work the same as polar coordinates in the plane. So we have an angle here, that's the first angle, phi, between the x1 axis and that point in question. And then we have a second angle, that's that angle psi here, that's the elevation above the x1, x2 plane, right? So from that point, let's make this here, yeah, we have this angle psi that basically says how far above are we over that x1, x2 plane. And then we have the radius, that is the length of this vector here. So this is the point here, okay? Now we need the upper half of a ball of radius 2 around the origin. Radius 2 is of course easy. We just constrain the radius to be between 0 and 2. So that's not the problem here. And then we have those two angles, phi and psi. And basically there's, the way we introduced it, let's say like this, the way we introduced it, there is more than one possibility to describe the same set of points using spherical coordinates. In many cases, you'll find a restriction of spherical coordinates to certain combinations of angles to avoid that ambiguity. I didn't explicitly introduce that, so basically you have a choice of what you'd rather do here. I opted to have that phi be between 0 and 2 pi. So first angle is that phi here. And I'm having that between 0 and 2 pi. So that means phi rotates around that whole x1, x2 plane. So basically we have a circle here in that x1, x2 plane. Yeah, so that means phi is between 0 and 2 pi. That describes that whole circle. And now if we also add this psi vector, as long as we keep it at 0, we are in the plane. And as we increase that vector, we are lifting our points. So for a fixed psi angle and a fixed radius, if we just vary the phi angle, then again we rotate around the x3 axis. So again, we get circles around this axis like this that are just lifted a little, okay? And if we want to describe the whole half ball, well, how far do we have to lift to get the whole half ball? And the answer is, well, this is about this psi here. The answer is once we lift up to the x3 axis, like 90 degrees, then the circle that we describe by rotating around that point, oops, sorry, is basically this single point here, right? If we increase the angle even more, yeah, we're getting somewhere here, then if we're rotating around this, right, if we for that fixed psi, again, let the phi vary between 0 and 2 pi, again, we're getting circles around the x3 axis, but those are the same circles that have already been described by a psi angle on the other side, so to say, of the x3 axis. Yeah, so this angle and this angle, these two psi's, those describe the same circle around the x3 axis. So the points that we would get through these angles are the same that we already had. And that means we would include the same set of points twice in our set D. And we don't want to count the point twice, because that obviously would modify the integral. We only want to count each point once. And that's why we have to stop at 90 degrees. And often, as I said, in the literature, you often find the restriction that this angle psi has to vary between pi over 2, 90 degrees, and minus pi over 2. Yeah, but you don't have to make that restriction, actually. You can also handle that a little more liberally. You just have to make sure to not hit the same point twice. And that's why I stopped at pi over 2 instead of letting it go over to pi. Now, you could also do that. Oops. You could also do that if you restricted your phi in turn. So the other option that you would have is you could say, I'll restrict my phi and I'll let that vary, not between 0 and 2 pi, but only between 0 and pi. Yeah, so that is phi equals 0, that is phi equals pi. So I'll only describe half of that disk in the x1, x2 plane. And I'll get the other half by just flipping it over using that pi angle, right? So this corresponds to pi equals 0 again. And again, if I start to lift this whole thing, like here, then I'm getting a half disk. That's hard to draw. Getting a half disk through that, like this. And of course, I can lift it up here. And that means I'll have half of that ball. And then I just flip over for psi values between pi over 2 and pi. I get those half disks again, but now on the other side. So that fills the other half of the ball, so to say. That means this would be the alternative. I could also say I get the same D by using R between 0 and 2. That's the same in both cases. I could then use phi between 0 and pi and psi between 0 and pi. Yeah, that's the alternative description. I could also use that. Just make sure you don't count any points twice. You have to restrict one of those two angles to make sure that happens. So you either have to restrict phi, as I did in this last alternative here, or you have to restrict psi, as I did in the suggested solutions, to avoid that double counting. Does that help? Or are there any more questions?
Yeah, there are. So there is one question concerning the previous exams, and the other ones are on the current exam. So maybe we can do the question on the previous exams first.
Yeah, let's handle that first, and then we'll close with questions about the exam.
Could you please explain how you came up with the parameterizations for the two curves in the previous exams?
I'll have to find the previous exam first.
So
Sorry,
it's a very specific question.
I don't have that ready right now, but I should have that somewhere. Just give me a second. So that should be summer of 17. We're talking about the first or the retake exam?
There's written in the previous exams, so I think it's in both.
Okay, I'll just have a look at the first one then. Is that right? Okay, so I'm guessing, Actually, do I have that on my iPad? I should have that somewhere. Here. I'm guessing you refer to that question number 2. Can you see that? Yeah, you should be able to see that. So where it says here we have a parameterized curve. And the question is to determine the parameters alpha and beta to get a suitable parameterization of that curve. I'm just guessing that's the right one. Yeah, if it isn't, just again, write to chat. Okay, so
yes, it is that one.
Okay, so what we have given here is that is the form of parameterization that we are looking for. And this here is the curve that we want to describe. Okay, and specifically we have the point 0, 0 here, and we have the point 0 minus pi here. T is between 0 and pi, so those should give us the endpoints. And that means the first thing I would try to do is have a look at those endpoints, right? So if that is, let's just call this gamma of t, that is gamma of t, then let's compute gamma of 0. That will then be alpha times, well, beta times 0 is 0, so we get sine of 0, and we get cosine of 0 here. So that does not even depend on beta. So what we have here is alpha times the sine is 0 and the cosine is 1, 0, 1. Okay. The other point is gamma of pi. That would be alpha times sine of beta pi and cosine of beta pi. So that, sorry, beta pi. So it does depend on pi. On beta, sorry. So we don't really know what point we'll get there yet. Okay. So how do we get the right parameters, alpha and beta, or maybe not parameters, the right expressions? You will notice I wrote suitable expressions and not parameters, suggesting that they might not be constant. Why did I do this? Well, if you look at this here, the point 0, 1 times alpha, if alpha is a constant, this point 0, 1, that would be here, 0, 1, and that would just be scaled then. Well, what would be a possible point, a possible endpoint here in the scaling? Well, either 0, 0, of course, or this one. So if alpha was constant, then we only have the choice between 0, which doesn't make sense because that would 0 out the whole curve, or minus pi. That also doesn't make sense because for minus pi, we would have a constant radius of minus pi here. You will remember, hopefully, that this expression here describes a unit circle with inverse rotation, so to say. So this circle rotates in this way. The usual cosine sine would rotate the other way around, this way. Just a second. But in any case, the radius of that circle, this circle here, that would be 1. And that means if we have a constant factor in front of it, we would get a circle with constant radius, radius alpha. That's not the case here. That's not a constant radius. But instead, the radius varies. So this alpha kind of describes the variation of the radius, obviously. And that variation seems to start at 0, at this single point, and then the radius increases. Up to this point here, where we have a radius of pi, right? So this alpha has to vary somewhere between 0 and pi. So what might be a good first guess? Well, if you have a look at how the radius changes, you can see, for example, this and this distance, or this distance and this distance, or also these two distances, those seem to be the same. So the variation of the radius seems to be constant. In contrast, for example, to the radius, the variation getting smaller or larger or whatever. It's always the same thing. So this alpha is probably a linear function. And that's basically all the hints that we need here to get a first guess that alpha might actually just be t. T varies between 0 and pi. That's good. It's a constant function, a linear function, sorry, so the variation should be constant. That might do nicely here. Again, it's just a guess at this point. We have to verify that this works later. Let's try and find a guess of the beta that we can make work with this here. What does this beta do? If the beta was not there, so if we just had something like sine t cosine t, you know what we would get then? That would just be a circle starting here and then rotating around once. If we vary t between 0 and 2 pi, in this case, we vary between 0 and pi, so we wouldn't even rotate around once. We would only rotate around for half a circle, like this. Now, if we have this beta inside there, what this does is it kind of speeds up the rotation, right? So for every unit of t, the argument of the sine and the cosine changes not just by the change in t, but by beta times the change in t. So if beta is some number greater than 1, that means the argument changes faster than the t. And this makes the rotation faster. So for example, if we had something like sine of 2t, cosine of 2t, and again, we let the t go from 0 to pi, the argument would in that same time go from 0 to 2 pi. So that would give us a complete circle. Okay, so how many rotations do we have here? Let's see. We start here. That's the first rotation we complete. Here's another full rotation. And then there's half a rotation. So what we get here is 2.5 rotations. Now we want 2.5 rotation while t goes from 0 to pi. A full rotation would mean the argument has to go from 0 to 2 pi. So in this case, the argument varies between 0 and, well, 2.5 rotations. One rotation is 2 pi, so 2.5 times 2 pi, that would be 5 pi. Yeah, so the argument needs to vary between 0 and 5 pi. If t varies between 0 and pi, well, the factor that we need is obviously 5, right, to get that variance. So beta, I guess for beta would be 5. Now we just have to check whether this all works using the 2 points that we've computed here. So if that works, we would start here for alpha equals t. Here, t equals 0, that would mean we have 0 times that point. So we would just have the origin correspond to t equals 0. So that would be this point here. Seems to work fine so far. Now what about the other one? Let's hope this works out as well. So if that is t, then we'd have something like pi here. And then we would have sine of 5 pi and cosine of 5 pi. That means we would get pi times, now the sine of 5 pi is the same as the sine of pi. That is -1. No, it's not, it's 0, sorry. The cosine of pi is -1. So we would actually get 0 minus pi. And that's just the point we have here, yeah? So this would correspond to t equals pi. Okay? So basically that's how I got these two parameters. First one is the radius, and the radius uniformly increases, so that's just a linear function of t. Second one is basically the number of rotations that we want. That's just a constant in this case. And I'm just using the endpoints to check whether this makes sense. And of course, in this question, you only have to write down your answers, so you don't actually have to explain your reasoning. Okay, I hope that answers this question.
There is another question on that exercise. How would our values change if sine and cos change positions?
If sine and cosine change position, then what happens basically is the start point changes. So again, if we have sine and cosine, then for t equals 0, we have sine of 0, cosine of 0. So we have 0, 1. That means the starting point of a circle like this would be here. And as t increases, the sine increases, so the first increases, whereas the cosine decreases. So we would get a rotation in this direction, right? So that is sine, cosine. If we use cosine sine instead, then the start point, cosine of 0, sine of 0, would now be 1, 0. So that would be the new start point here. And as t increases, the cosine would decrease. So the x1 coordinate would now decrease, and the second coordinate would increase. So it would get is a rotation in this direction. That's the difference. So the start point is different, and the direction of rotation is different.
Okay, I think we can start with the questions on the exams.
Good. Let's start with the questions on the exams.
There was one Moodle quiz where Fabian and I used some identities with cosine of 2 of x, and Jérôme Müller asks whether there will be exercises where we need to use trigonometric identities we have seen so far, either in the lecture or on the exercise sheets, or do you plan to add some we haven't used yet?
So basically, if you know the ones we have used that, then you should be fine. If I want you to use something else, I will tell you so. So there would be a hint in the problem statement saying this might be a useful identity. Generally, the one identity I would expect you to know by heart is sine squared plus cosine squared is 1. And for all the others, I would usually provide a hint.
Is there anything additionally we need to do if we are to use the given template for the exam on which we write the solutions?
I'm not sure if I got the question correctly. So you use the given template for the, so you download the template when examination time starts, you fill in your solutions, you upload the result, of course, and then you just have to keep your fingers crossed and wait until we correct it.
Yeah, maybe the question asks for whether to write its name on the template or not.
You don't have to write your name on it. Yeah, there will be a feed where you can sign, but that's it. Yeah, you sign a very short version of the code of conduct that basically says I have read the code of conduct and I understood it, and I confirm that I will keep to that code of conduct. And of course, you will have to successfully complete the preparatory exam. If you're using your own sheets, there's a little more to that. So if you plan on using your own sheets, please download the templates that are provided on the Moodle page. We will not accept anything other than those templates. So please print those out and have them ready if you want to use your own sheets. And on those templates, I'm asking you to also fill in your name and your student ID number on each of those, so that we can make sure that nothing is being mixed up. but that's it.
Maximilian Eichler wrote, there are some integrals that occur quite often or are maybe hard to solve. Some of these are integral of sines of t over 2 or similar. These integrals would have been on his cheat sheet if the exam was a normal exam. Do we still have to solve such integrals by substitution or integration by parts, or can we just use the solution which would have been or will be on my cheat sheet?
So anything we didn't explicitly do in the lecture or in the exercises, you will either have to explain, or if the problem statement asks you not to explain anything, so if I just want the solution, then of course you don't have to do any explanations. But if I ask for documentation, justification, explanation, then you'll have to explain anything that is not in the lecture or on our exercise sheets.
Felix Fechner asks, there is the following statement made in the assignment sheet of the test exam. If applicable, please also add your certificate of matriculation here. Do we actually have to add the certificate of immatriculation?
So most of you will probably use your student card for identification. If you're using this, then you're good. That only applies if you use some other method of identification. That doesn't automatically include a certificate of immatriculation.
Do you suggest doing the previous exams? Will our exam look similar to the previous ones?
I wish I knew. I'm in the process of finishing the exam currently, so I can't really give you a well-substantiated answer here. Probably yes. But of course, I'll have to adapt it somewhat to this new open book situation. You'll understand that.
And now there is a clarification for the exam templates. The ones that are already given are meant for those people who don't have a printer.
Right. So the exam templates, the templates that I uploaded on Moodle for you to use if you want to use your own paper. So those templates are meant to be your own paper. So if you don't have a printer at home and if you have no means of submitting electronically using an iPad or something similar, then you can use those. Just download the PDF, print out the pages, and during the exam, write on those pages. You can fill in your name and your student ID number beforehand. And please make sure to use each page number only once. But basically, that's it.
And there are two questions concerning the methods to use. So just to cite Julius Mears, do we always have to use the procedures as done in the lecture? There are, for example, other ways of solving some things, for example, Grange exercises.
So if you're using other means, then of course you can do that, but you have to explain your reasoning. I mean, if you're using some theorem that we didn't actually have in the lecture, then you'd have to provide a proof for that, for example. Or if you're using some other methods to calculate something, again, you have to explain your reasoning behind that.
Do you plan to make a deadline for the Moodle test? So are they still available after the exam?
I'm guessing you didn't implement any deadlines, did you?
I didn't. I
so
think
I don't.
Fabian didn't either.
Good. I don't plan on doing that. No.
Okay.
So they will be available after the exam.
Okay, I think you've answered all of the questions. I hope I didn't miss something. If so, no,
okay, great.
Yeah.
Good. So if anything comes up, you're welcome to still write to our chat, of course, and we'll try to answer, or you can also use the Moodle forum. Again, we'll try to answer anything. Please try to not hold off until the last night before the exam. I'll probably need to get some sleep as well, and you also should. Okay, good. So if there's no more questions, then thanks, Katrin, for doing the moderation. It was a big help. Thank you all for attending, and good luck for the exam, of course.
Good
I'll
luck.
see you then in a virtual way. Goodbye.